Welcome students. This presentation will be on chapters 4 and 7, and specifically with respect to inclined planes. I appreciate you coming to Second Life to learn this lesson, and we'll be going into more details of inclined planes with respect to adding friction and making sure all the forces are balanced in equilibrium. This is a graphical representation of an object in static equilibrium, which means that the object is at rest and all the forces acting on the object are balanced against each other, resulting in a net force of 0. As you can see in the diagram, we have a normal force, which is the force acting in opposite direction of the weight component applied to this inclined plane. And in order for this object to stay on the inclined plane, we need some kind of balancing force, which is a friction force, which we'll talk about in more detail later. Now, forces can be of three types: applied forces, non-applied forces such as weight, and forces replacing a support, also called reaction points in or a sectioned member. Free body diagrams must be used for all force problems. They must be 100% accurate with magnitudes and directions displayed. They must also include all the forces acting at a point, and they must be checked before the problem can be solved. Now, in order for static equilibrium to exist, we must have the following three conditions. All the sum of the forces in the x equals 0, sum of the forces in the y equals 0, and all the sum of the moments have to be equal to 0. And if we were dealing with 3D, we also would add the sum of the forces in the z direction, also have to equal to 0. Now, in physics, Newton developed his fundamental kinematic laws, which are better known as Newton's laws of motion. Now, they are the following. Newton's first law, which states an object at rest or in motion will continue at rest or in motion until acted upon by an outside force. Newton's second law says the acceleration of a body is directly proportional to the force acting on the body, which gives us the formula force equals mass times acceleration. And Newton's third law says for every action there's an equal and opposite reaction. Now, with regards to friction, all three laws apply. Not only is friction a force, but it acts to change motion or decelerate, and it also is considered a reaction force due to the contact between one surface and the next. Now, several rules exist with respect to friction forces. They must be parallel to a flat surface or tangent to a curved surface, must be opposite in direction to the motion or impending motion, must be dependent on the force pressing the surfaces together. In most cases, this is the weight of the object. It's generally independent of the area of surface of contact. It's independent of velocity, except for extreme cases, which is not to be considered in this chapter. And it's also dependent on the nature of the contacting surfaces. Now, what does impending motion mean? Well, this means that the object being analyzed is on the verge of moving. If we add an additional force, the object would cause motion. But this object, if it is not moving, is in static equilibrium. We still need to draw a free body diagram. Now, can friction forces be exerted on bodies in motion? Of course. If you think about a car driving down a street and someone hits their brakes, friction works to slow the car down. Now, dealing with coefficients of frictions, let's recall some laws of friction. First, they must be parallel to a flat surface or tangent to a curved surface. They must be opposite in direction to the motion or impending motion. They must be dependent on the force pressing the surfaces together. In most cases, it's the weight of the object. And they're also dependent on the nature of the contacting surfaces. Now, let's look at one of the most basic examples, the block. Now, every object has a mass that has weight, which is concentrated from the center of the mass of the object. But if that object comes in contact with the surface, then the surface must react in the opposite direction of that force. And this is called the normal force. But what if we subjected the block to an applied force P? And what would happen is, depending on the surface of both the block and the ground, the object does not move, or is in static equilibrium. We could say we have a force going the opposite direction of P. This is known as the frictional force, F. Now, the friction force is depending on the normal force, which is dependent on the weight. In fact, the friction force is directly proportional to normal force by a constant known as the coefficient of friction, mu, which is dependent on the surface properties like rubber on concrete, concrete on concrete, etc. And the equation that is used often for this friction force is the friction force equals mu times the normal force. or mu equals the friction force divided by the normal force. Now I need to take a step back to discuss how to calculate weight. The book gives you mass, then you need to create the weight in the value of newtons. Now weight equals mass times the acceleration due to gravity. And gravity in this case is using 9.81 meters per second squared, or in English units is 32.2 feet per second squared. Now on a flat surface, this is the normal force. But what you'll see when you watch some other videos, that this particular force will change, the normal force will change on an inclined plane. Now what I'd like for you to do is watch the two videos that are located within this same player. By the next class meeting, I want you to turn in the following problems, and you must also include your free body diagrams for all the problems. Problem 7-4, 7-24, 7-25, 7-31, and the review problem 7-6. Good luck!